I am going to talk today about how one can do astronomy by using archival data. I work at the National Center for Radio Astrophysics in Pune in India. So, let us get started. We will begin by giving you a brief history of archives in the field of astronomy. The story begins nearly 2000 years ago with a Greek astronomer named Hipparchus, who first decided that he should make a catalogue of the stars that he saw in the night sky. He constructed such a catalogue, he made up some constellations and he recorded it. So, this probably represents the earliest attempt at creating an astronomical archive. So, when we say astronomical archive here, what do we mean by an astronomical archive? We will take a very simple definition, which is any kind of organized, systematized information about the sky above us, we will call as an archive. Of course, the earliest archives at the time of Hipparchus were very, very tiny. The catalogue of stars that he created and the constellations that he listed could probably have been noted down in a few pages of text. Today's archives are many terabytes and sometimes even petabytes in size. They have grown enormously over the last 2000 years. The next important person when we think of regularized, systematized recording of astronomical information, the next important person is the Danish astronomer Tycho Brahe, who you see here towards the right in the right panel. And Tycho was interested in actually cataloging the positions of the naked eye planets as a function of time relative to the stars which were fixed in the night sky. So, over the years in the late 1500s, using his own observatory, he made many observations of the positions of the planets in the night sky. Some decades later, the great astronomer Johannes Kepler used these observations in order to verify his laws of planetary motion. You may be aware that Kepler was the first person who showed that the sun was at the center of our solar system and the planets moved around the sun in elliptical orbits. And he computed the laws of planetary motion, which he then tested using Tycho Brahe's archival observation. So, this probably represents the earliest attempt at using archival data to do actual astronomy. And of course, Kepler's work was fundamental in altering our view of the solar system, where previously people had believed that it was the earth that was at the center of the solar system. And now along came Kepler and used the archival data of Tycho Brahe and showed us for the first time using very accurate observations that Brahe had achieved at that time in spite of not having access to telescopes. All of Tycho's observations were made with the naked eye. As time went on, particularly in the telescopic era, catalogues of various kinds of objects began to serve as important archives of astronomical data. In 1603, Bayer he compiled his star catalogue, and for the first time he thought of an idea of labeling every star in a constellation by its brightness. So, he partitioned the entire sky into several constellations, and in each constellation he labeled the brightest star in that constellation as alpha, the second brightest star as beta, the third brightest star as gamma, and so on. And he constructed the first sort of star atlas and a accompanying star catalogue that tried to classify stars as per their apparent brightness. More than a century later, the French astronomer Charles Messier compiled his catalogue of nebulous objects in 1771. The purpose of Messier in compiling this catalog was to provide comet hunters with a list of well known extended nebulous kind of sources in the night sky, which could frequently be confused with comets. So, Messier's catalog had about 100 objects, in which he had a motley collection of what we know today to be gaseous nebulae, galaxies and star clusters, both open clusters and globular clusters. This was an important catalog and is still being used today by amateur astronomers who like to hunt down the Messier objects in the night sky. By the time another century had passed, in the year 1888, Dreyer had compiled the NGC catalog, New General Catalog, and it had more than 7,000 objects. So, we are talking of now going from several hundred objects to several thousand objects. At this point, we should also remember that the information that is being recorded is being recorded now in a very disciplined, very systematic way and in a very reproducible way. So, all the information that is recorded can also be checked out by other people with their own telescopes. This represents a fundamental change in the way of doing astronomy, because for thousands of years astronomers in many countries across the world had recorded one-off events, like for example eclipses or supernovae, or in some cases comets that appeared in the night sky. But these were one-off events and were not terribly useful as an astronomical archive for future astronomers. But with the advent of Dreyer's NGC catalog and Messier's catalog and so on, it became now possible for astronomers to study the night sky and even the day sky in a systematic way. The next major development in astronomical archives came with the Palomar Observatory Sky Survey, and it was carried out at Mount Palomar in California in the United States, and it was carried out with this particular telescope that you see in the background, which is referred to as the 48-inch Schmidt. This telescope is characterized by a very large field of view, and by putting large photographic plates or at its focal plane, it became possible to image large parts of the sky at one go. So, all you had to do was to load a photographic plate at the right position, point the telescope to the part of the sky that you wanted to observe, and observe for a few minutes while the telescope tracked the sky, and then take out those plates, process them, and then you would have a photographic evidence of the night sky. The person you see standing in the foreground is Edwin Hubble, and he of course discovered the expansion of the universe, and this photograph was taken a few years before his death. The Palomar Observatory Sky Survey produced large photographic plates, which were then reproduced and taken to various other observatories of the world. So, these were reproductions in glass, they were very delicate and had to be handled carefully, but they represented an archive of the night sky. The Schmidt telescope that you see here was able to observe the entire northern sky, and for the southern sky a similar campaign was carried out a few years later, and that allowed us to have a complete glimpse of all the stars and galaxies in the southern sky. Let us now look at the role of technology in the growth of archives. Already technology had played an important role in the Palomar Observatory Sky Survey, because without the use of fairly sensitive photographic plates, it would have been impossible for us to carry out such a large area sky survey. But in more recent years, it became possible to use digital technology in order to make very rapid progress in both the quality and quantity of astronomical archives. By the 1990s, scanning technology had improved to a point where it became possible to take the Palomar Observatory Sky Survey glass plates, put them into a machine like the one that you see here, which could scan photographic plates and produced a digital image which could then be distributed far more easily. In fact, in the 1990s this was done and the entire Palomar Observatory Sky Survey became available as a set of about I think 90 CD-ROMs which were distributed all over the world. These were of course much cheaper to reproduce than the original glass plates. So, it became affordable now for many people to have a glimpse of the night sky as seen with these plates. One more important technology emerged in the 1970s and by the 1990s had matured, and that was the growth of digital detectors. What you see here on this plot, on the x axis is wavelength marked in nanometers and on the y axis is the quantum efficiency of the detector. And what you see in the upper curve is an example of a back thinned CCD, a device, a charge coupled device that was an electronic solid state detector that could detect light directly and directly record the information on a computer. So, it became possible now to gather digital data directly, and of course, digital data is much better than digitized data because it suffers from none of the shortcomings that the analog processes are prone to. You can see here that between about 400 nanometers and 800 nanometers, the quantum efficiency of the back thinned CCDs remains above 70%. So, which means if 100 photons reach the detector, 70 of them are actually detected. This means that you have a 70% efficiency, and that means that you can hardly do much better than this. This compares very favorably with the photographic plates, which in this range had a quantum efficiency of about 10 to 20%. So, this was a dramatic improvement in the sensitivity, which meant that any given telescope, if you replace the photographic plates in it with charge coupled devices, your sensitivity suddenly improved by 3 or 4 times without doing anything else. These charge coupled devices also had one very important property, and that is their linear response. What that means is, if you doubled the light that you shone onto a CCD, its output, which is the voltage that it produced and the digitized counts that it produced, would also double. If you quadrupled the amount of light that you threw on the detector, then the output would also quadruple. This means that calibration of the CCDs is extremely easy. Unlike photographic devices, where the response curve is not a straight line like the one you see here, but is extremely nonlinear, which makes the job of calibration extremely difficult. Developments in CCD technology in the optical have been mirrored by similar developments in other wave bands. So, if you take radio interferometers, which are the most popular kind of radio telescopes, the development of optical fiber signal transport, the development of software correlators and low noise amplifiers have had a similar effect that CCDs have had in optical astronomy, in that they have enabled orders of magnitude growth in the quality and quantity of the astronomical data. Accompanied by these advancements in astronomical technology, there has been this rapid improvement in the field of computing. So, what is shown here is a representation of Moore's law, which shows on the x axis is the time, is the year in which the we are talking about going all the way from 1970 to 2016, and on the y axis on a logarithmic scale you see the number of transistors that were available in the best CPU available in that particular year. And you can see that we have gone from the Intel 4004, which had somewhere between 1000 and 5000 transistors on the CPU, to devices that have of the order of 10 billion transistors on a single CPU. So, this dramatic improvement in computing technology has obviously benefited astronomy, because now we can process data that much faster than we could do previously. Such improvements have also occurred in the amount of random access memory that typical computers have, and in the amount of storage that one can have, and also in the cost of all of these components. There has been a dramatic improvement, and because of that we are able to now store and process unimaginable amounts of data at the present time. So, there are, I feel, broadly two threads for the new developments. The first thread is related to the developments in digital electronics and the developments related to CAD/CAM technologies, computer aided design and computer aided manufacturing technologies that have enabled us to make dramatic improvements in the kinds of telescopes that we build and the speed and cost with which we can build them. And of course, as I have already mentioned, the developments in computing technology have also been nothing short of dramatic, and these have both resulted in a big increase in the quality and quantity of digital archives in not all disciplines, including that of astronomy. There is one more aspect which is very important in the handling of archives, archival data, and that is the widespread access to high speed internet connections, which has become popular in recent years, and it has made these vast archival data sets accessible to a much larger community. Until the coming of the internet, even if there was a lot of data, it was typically with the people who had access to the largest telescopes of the world. People who did not have access to the telescope simply could not get their hands to the data unless they traveled to the telescope or to the institution which hosted that telescope and got access to the data. But now, because of the internet, it becomes possible for us to develop large computer archives in which the data are stored, and typically they are kept private to the people who have proposed to observe that particular object for a certain period of time, say a year or 18 months, and after that, that archival data is open to the public. And when that happens, it becomes accessible not only to astronomers from less privileged countries, but it becomes accessible to large community of non-astronomers. And this has enabled a large number of citizen science projects which use these large data archives. And here is one example of a citizen science project which is known as Galaxy Zoo. In Galaxy Zoo, what people do is that they have a large catalog of galaxies, galaxy images, which they show to users, and they ask them to classify every galaxy that they are shown as a smooth galaxy or a galaxy with spiral features or a disk, or something that looks like bad data or an artifact. And this has been done for literally millions of galaxies, and hundreds of thousands of users across the globe have put in their time and effort in order to classify galaxies in this way. So, without the combined power of a large data archive, in this case the archive of the Sloan Digital Sky Survey, and very democratic access to the internet, these kind of citizen science projects would not have happened. But today they are commonplace. This is just one example of a citizen science project using astronomical data. There are many more examples in astronomy itself and in other fields of science too. There are great efforts going on in order to use citizen science in order to further the particular science that people are working in. Let us now talk about some of the software tools that one needs to access the data archives. So, fine, we have very large data archive, they are now commonplace in astronomy. How do we know what data are available and how do we search for these data in these very large archives? It may become a problem like searching for a needle in a haystack. When there is so much data, how do we visualize these large data sets? And how do we combine multiple pieces of information that is in different locations in the archive? Are there a common set of software that one can use in such a situation in order to extract all this information? It turns out there are a number of software tools that have been developed to support all of the above activities, and I will now introduce you briefly to some of these one by one. Note that I only have time to introduce you to the most commonly used tools, those that are used by almost every astronomer. There are many other more specialized software tools that I will not be talking about, but if you work in a very specialized field, you will surely come to know about them, and they do exist and you can use them. So, when one starts doing research in astronomy, the first thing to study is what is the available information on that particular topic of research, right. We refer to this in any science as a literature survey. In order to carry out a literature survey in astronomy, an important archive is there. Its name is the SAO NASA Astrophysics Data System, or ADS for short, and what it is a digital library portal for researchers in astronomy and physics. The ADS maintains the bibliographic databases, and today they contain more than 14 million records covering publications in astronomy and physics, astrophysics, in physics and in the archive e-prints. The deficiency of some of our journals today is that they only allow access to users who have a license to view the papers. This may come individually or it may be provided by the research institution where people work, but many of the journal papers are not directly accessible. To overcome this problem, some decades ago, the archive arxiv.org site was developed, and this provides open access to more than 1 million e-prints in physics, mathematics and several other subjects which you see listed here. Archive.org is a way of getting a free copy of a journal paper for which you may not have direct access. Archive.org papers are also searchable through the ADS, and if you know the title of the paper or a keyword that describes the paper or the name of one of the authors, etc., it becomes very easy to go to this website adswww.harvard.edu and search and download papers in the field of your interest. Naturally, there are mirrors of the ADS site which are located all over the world. Once you download your research papers and you read through them, at some point you will discover in some of the papers a large catalog of a certain kind of object, okay? And let us say you want to access them for further analysis, and this is made possible through the Vizier website, and again which is mirrored all over the world, that allows users to gain electronic access to such catalogs. The query tools in Vizier allow the user to select the relevant data tables and to extract and format records matching the given criteria. Currently, more than 17,000 catalogs are available through Vizier. These catalogs may be downloaded in a variety of formats, and they could be downloaded from any of the mirror sites of Vizier. So, let us now take a break and go and look at how Vizier looks, and I am going to load the Vizier website. So, when you go to Vizier, you can search by the name of a catalog or the name of an author. Let me search by my own name, and when you click on find catalogs, it shows you a list of the various catalogs that have been authored by this particular author, in this case me. And what you see here is a list of catalogs. So, every row represents one catalog. It tells you what is the unique identifier for the catalog, that first column J, A plus A slash etc. It tells you approximately how many records are there in the catalog. So, for example, the first catalog has 2,844 entries, and it tells you in a short phrase or sentence what is the nature of that catalog. This, if you click on the name of a particular catalog, if you click on Vizier access through Vizier, what loads up is a description of all the columns in the catalog. Okay. So, what you see here is, first of all, there seem to be two tables in this catalog, okay, AGN with radio detections and AGN not detected in the radio, right. There are two entries there, and then that is followed by a detailed description of all the columns that are there in that particular catalog. Right. If I go to the top right and I click on this read me plus FTP, then it gives me direct access to the catalog. It tells me shows me the abstract of the paper from which this catalog was taken, and it gives me direct links to these two catalogs which you see here, table 3 and table 4, and I could then, if I so chose, actually download the catalog and look at it. We are going to see how catalogs can be analyzed, archival catalogs can be analyzed, but this is the basic purpose of Vizier, that if you have a catalog that is published in any journal, in any paper, in any journal over the last 20 or 30 years, then that catalog is available to you in Vizier, and therefore, you can use it in order to download it and carry out some analysis. You have downloaded the catalog, what do you do with it? In order to visualize data in a catalog, there is a tool known as TopCat. TopCat is basically an interactive graphical viewer and editor for any kind of tabular data. So, a catalog that you download would qualify here, and its aim is to provide that most of the facilities that astronomers need for analysis and manipulation of source catalogs and other tables and so on. It understands a variety of different astronomical formats, including FITS, VO table and CDF, and even more formats can be added. What is FITS? FITS is the flexible image transport system, which is a standard that was defined by astronomers many years ago in order to ensure that data taken at one telescope can be used by anyone, any astronomer anywhere in the world. So, FITS was originally a format for exchanging images or storing images, but now it also includes the capability to store tables, which means catalogs of objects. So, both catalogs and images can be stored in the FITS format, and TopCat is a tool that will understand tables that are stored in the FITS format. It provides you with a variety of ways to view and analyze tables, including a browser for the cell data themselves and viewers for information about table and column metadata, and some facilities for fairly sophisticated visualization, calculation of statistics about the columns, and also for joining two tables together. Using a powerful and extensible Java based expression language, new columns can be defined and row subsets selected for separate analysis. Table data and metadata can be edited, and the resulted modified table can be written out again in a wide variety of output formats. So, just like TopCat can read data in various formats, it can also write out data in a wide variety of formats. It is a stand-alone application which works quite well even without an internet connection, but since it uses something known as the virtual observatory standards, we will see in a few minutes what those standards are, it can operate smoothly with all other tools, services and data sets in the VO world and beyond. The program is written in pure Java and therefore can run on any operating system that can run a Java virtual machine. So, let us now go and take a quick look at TopCat. So, I have downloaded the TopCat tool and it is installed on my machine over here. I am just going to type TopCat and I am going to give it the name of a catalog that I have. It is in FITS format and it is a zipped catalog. However, TopCat happily understands zip files and can open them for you. So, what you see here is the name of the catalog. I click on it and then I get a table which lists for me all the various columns that are there in the catalog. So, with this now I am able to browse through the data that is there in my catalog. It has all kinds of columns, we will not go into that, but what one can do now is to try and visualize the data that is contained in this catalog. In this table of properties, you get a summary of the main properties of this particular catalog. You can see its name, okay, and what is its file name, and you can see the number of rows it has. It has about 2320 rows and 13 columns. You can of course sort it in various orders, you can ascending or descending and based on any of the columns. We looked at the data in the catalog. Let us say for example, you want to plot up some of the data. So, I click on scatter plot, that loads up this, and here at the bottom I specify exactly what I want to plot. So, let us say on the x axis I plot the right ascension, which is the equivalent of longitude in astronomy, and on the y axis I plot the declination, which is the equivalent of latitude in astronomy. And what do I see here now? I see these little red dots which correspond to every object in my catalog as it would appear in the sky. So, on the x axis I have the right ascension in degrees and on the y axis I have the declination in degrees. So, I have chosen these two, but you could plot any other parameter against any other parameter. All of this is very customizable. I have this grid, I could get rid of the grid, I could change the color of the data points, I could change their size, I could change the marker symbol used. This is just like a dot or a square. Right now, I could make it an open circle or a filled ellipse or whatever. It also allows you to make histograms of any parameter that you want. So, for example, this is a histogram of XID, but I could make a histogram of the fluxes. So, what we see here is on the x axis is the 250 micron flux in millijansky, and on the y axis is the number of sources that have a flux within a certain range of fluxes as shown here. Again, this histogram can be endlessly customized. You can change the range, you can change the bin size, you can change the number of bins, and you can change the colors, the line styles, and so on. You can also do limited amount of 3D visualization. No, this is not what I want. You can plot things in 3D. So, you could have, let us say, array on the x axis, the declination on the y axis, and let us put the flux, which is this F250, on the z axis. And you have this little cube which can be easily rotated, so that you can gain a 3-dimensional view into the data points. You can see here readily that the number of sources that are very bright, that have fluxes say above 250 millijansky, are very few in this catalog. Most of the sources are very faint. So, this gives you a complete 3-dimensional representation of these parameters. So, TopCat is a very powerful, easy to use tool. You can just download it off the internet. It is very easy to install. So long as you have a working Java environment on your computer, it allows you to handle catalogs in a very seamless way, allows you to make selections of various kinds, okay, and then allows you to even write out your selected catalog into a separate file. We will come back to TopCat again when we talk about how TopCat can intercommunicate with other tools, and the other tool that we are going to talk about now is called Aladin. Okay, so you have got catalogs, but more often than catalogs you will have images of the sky which could have been taken with any telescope. So, if you have observed with a radio telescope, you will have large number of radio images. If you have observed in the optical, you will have optical images, and so on. In order to see these images and visualize them in a better way, a tool named Aladin has been developed. Aladin is basically an interactive sky atlas, allowing the users to visualize digitized astronomical images of full surveys, superimpose entries from astronomical catalogs or databases, and interactively access related data and information from a variety of databases like Simbad, Vizier, which we have already looked at, and other archives for astronomical objects in the field. Okay. So, let us say you have studied a particular portion of the sky and you want to understand all the objects that are there in your field of view, and you want to gather information about those objects, you can do that quite easily using Aladin. So, let us now spend some time to look closely at the kind of features that are provided by the Aladin software. So, again I have an image that I am loading up. So, what you see here on the screen is an image of a radio galaxy that was observed with the GMRT. So, this is an image that I have produced from archival data available in the GMRT data archive, which I will describe in a few minutes. But right now we have this image, which is a radio image. What you see here is at the center is the radio galaxy, the optical host of the radio galaxy is located here, and there are two jets coming out in opposite directions, and when they collide with the ambient medium in the presence of a magnetic field, they get decelerated, they produce these giant lobes, and these giant lobes are emitting quite brightly at radio wavelengths. So, this is a typical radio galaxy. We have displayed it. Now, what are the things that we can do with Aladin? So, first of all, I am moving my mouse around, and by moving right clicking and moving my mouse around, I am able to change the image and image brightness and contrast. If I want the image to look somewhat nicer, I go to this menu, image, pixel, contrast and map, and first thing I might want to try is to change the color map perhaps to rainbow. Now, you can see the radio lobes quite clearly. This now represents a false color representation of the radio galaxy, and at frequencies or bands outside of the optical, it is quite common to work with these false color images. By using the middle mouse scroll bar, I can scroll with the scroll wheel, I can zoom in and zoom out into this image. So, now I have zoomed in into the image, and now you can clearly see the core of the radio galaxy, and on the other sides you can see both the lobes on either side of the core. Now, this is already very interesting, okay, but there are some other additional tools that Aladin provides. For example, there is a useful tool called distance. Okay. So, I click on the distance tool, and let us say I want to measure the distance from the center to this hotspot on the left. Okay. So, I draw this line and I leave it, and I get this little drawing, this straight line with an arrow at the end, and this number over here 9.253 arc minutes, which tells me what is the distance between the center of the galaxy and one of the lobes. I could of course measure distances similarly for any combination of objects in this particular image. The other beauty of Aladin is that you can actually combine information from your own data with information that is available at other wavelengths. So, I go to the bottom left, okay, and I search for a data set called pan stars, and here in the archive I chose the wrong one. Okay. So, what I have done now is I have loaded up on the right panel an image of taken with an optical survey known as pan stars. It is possible in Aladin by clicking on this icon at the bottom left where I am now. If I click on this match icon, then I actually get a map of the same part of the sky in both the panels. So, on the left panel is the image of the radio galaxy as seen by GMRT, which we have just made it more colorful, and on the right panel is an image of the same part of the sky as observed with the pan stars survey. So, it becomes immediately apparent to me that the source of that line, which yellow line which I had drawn to measure distances, starts out with a galaxy over here. So, I can now zoom in and you can readily see that the emission that you see over here on the left in this dark blue color seems to be emanating from this beautiful elliptical galaxy which is sitting at the center. The arrow that you see in the right panel indicates the distance between that particular optical galaxy and the radio lobe to the left. This particular galaxy is what is known as a giant radio galaxy. So, it is extremely large in size, more than a few million light years across, and because of that it is much larger, the radio lobes are much larger than the optical extent of the galaxy that you see in this particular image. Now, so there are what more can we do with Aladin? With Aladin, one can also use it like a entire sky atlas, and we are going to do that by shifting now to a single object view kind of thing. And what you see here is at the center is of course is our radio galaxy, and surrounding it are many thousands of stars and other galaxies. I can begin to now zoom out, which I am doing, and as I zoom out, Aladin is loading for me from the PanSTARRS data archive. It is automatically loading for me images of larger and larger parts of the sky. So, I have zoomed in quite a bit now, and that bright pattern that you see here is the disk of the Milky Way, right, and one can zoom in now back again perhaps to a region where the Milky Way is at its densest, the number of stars are very numerous, and we zoom in, and as we zoom in, smaller and smaller portions of the sky are now automatically loaded from the PanSTARRS database. So, this becomes therefore a very effective technique for you to simply browse through large areas of the sky, even if you do not have anything particular to look at. Let us now go back for a minute to our radio galaxy. Single click brings me back to the image of the radio galaxy, and I will show you a tool wherein I am going to now construct contours of this particular radio emission in the radio galaxy. So, I go to overlay and I choose contour plot, okay, and here it asks me how many contour levels I should generate. I ask it to increase it a bit from the default value of 4 to 6, okay, and I am going to start moving things to the left, so that you do see some of the contours. And I click on get contours. So, it is over plotted a large number of contours. The first contour is very corresponds to a very low level of intensity, and therefore is a bit problematic. So, let us go back and try to change that. By changing, right clicking on the contours and clicking on properties. Okay. So, first thing I am going to do is I am going to remove the first contour and perhaps even the second one, okay, and we will keep the second contour. We can change the levels now. I am going to bring the lowest level to very low value, bring the second level further down, third level further down, and fourth level further down, fifth level further down, and so on. Once I do that and I click on apply, so there is one more feature that I would like to show you with regard to the radio galaxy that I showed previously, and that is how to draw contours on images. So, I have loaded the image of the radio galaxy again, it is back in that grayscale color. What I am going to do now is click on overlay and click on contour plot. When I do that, it asks me how many contour levels to generate, and then I can pull the contour levels to whatever level I want. I am trying to lower it so that we get a number of contours in the radio lobes. I click on this consider only current zoom, and what that does for us is that it will only try to build contours in the part of the image that we are looking at. So, what I do then is click on get contours, and there we are. So, a number of contours have been generated and plotted on the image. What we can do now is go click on properties and change some of the properties of the contour. So, the first thing I am going to do is to make the colors somewhat brighter. So, I will go with red, and then for the lowest contour, and blue for the next one, and somewhat bright green for the third one, and maybe black for the fourth one, and so on. If I click on apply, it has now changed the contour levels for me. The contour that I have at the lowest level, I am going to just move it a bit to the right so that it becomes a little less. It only shows me the lobes, it shows me the core that you see over here, and the two lobes, and they are now nicely contoured. So, here now you are seeing very nice image contours. It is possible to only see the contours. So, what I can do now is switch off the image, and now we are seeing only the contours that are overplotted on this gray background. I can also show these contours on another map. So, let us go back to a state where we had loaded the image from pan stars. I am going to select it again and search for it. I click on the match icon, it matches the scales and orientation, and I put my image back over here. There it is. I zoomed in quite a bit. So, there you are. So, now what we are seeing is the contours that are overplotted not only on the image of the radio galaxy, but also on the image of the optical pan stars image that you see here. We can zoom in further. Let us do a match and zoom in a bit further, and there now we begin to get a complete picture of what really is happening. Okay. So, there is this galaxy here at the center, which is the elliptical galaxy from which this emission is coming out. You can see some of the contours to the left over here which show that emission, and then that emission is eventually dispersing into this cloud of plasma, which corresponds to the radio lobes of the radio galaxy. The radio galaxy itself is completely invisible in the optical. It is visible in the radio, but only these contours from the radio tell you that there is something happening there. Aladin has one more really useful feature. If you go to a certain position on the image and hover over it, what Aladin does is that it tries to search for sources in the Simbad database that correspond to that position. So, this particular radio galaxy that we are looking at is of course a well known radio galaxy. It has an entry, and if I go and click on this, it will load up a browser, it will connect to a database known as Simbad, and it will provide me information about this particular galaxy. So, with a single click I am able to see the galaxy, see its optical image, see its radio image, see the radio contours, and now go to a website and gather information about that galaxy. So, here is some information about its position, and further down there is some information about its redshift. So, we know for example, that the redshift of the galaxy is 0.05 something, right. So, I can go back, I can do this with any other position, but what we have seen here now is also at the bottom right corner, it quickly shows you the photometry, which means the flux of this particular radio galaxy in various bands going all the way from ultraviolet to the radio, and it tells you how bright that galaxy is. Now, this particular galaxy is a very bright radio galaxy, it will be detected in most of the bands, and there you have those little data points at the bottom right telling you what those values are. So, at a glance it becomes possible for an expert astronomer to make some diagnosis about what a particular object that they are looking at. Right. Even in this image it is possible to change image and contrast. So, it is possible for example, to make really pretty images. Let us go back to the single view image. Okay. So, by just changing the image contrast, I will be able to change the view and make really pretty images of the object that I am interested in. So, this is our tour of Aladin. We are going to come back to both TopCat and Aladin in a minute, and we will look at how these two tools can interoperate with each other to give you even more insight into astronomical data. Aladin by itself is very useful, TopCat by itself is very useful, but using a technology known as SAMP, it becomes possible to combine the features of both of these. Okay. So, for example, it is immensely useful to be able to plot catalog positions onto an image, perhaps one obtained from at another frequency. Aladin and TopCat can work together to enable such analysis. So, what I am going to do now is I am going to load an image of a particular part of the sky in Aladin. I am going to load two catalogs of the same part of the sky in TopCat. I am going to do some combination, I am going to do a matching process on those two catalogs, and then I am going to export the match catalog from TopCat to Aladin. So, this sounds fairly complicated, but as you will see, this is extremely easy process thanks to the interoperability capabilities of the SAMP protocol. So, we begin by loading two catalogs. So, let me start TopCat. So, here TopCat has started up, it asks me what catalog I want to load. I choose two local files. This file 6 sigma XMM LSS catalog deg.fits is a catalog of all the radio sources, all the relatively bright radio sources in a certain part of the sky known as the XMM LSS field. I have loaded up that one catalog. Now, I am going to load another catalog. This is called this L6 XMM LSS SWAYAM. So, this is now an image, it is a catalog of the same part of the sky, but one obtained with a far infrared telescope named Herschel with the Spire instrument on Herschel at a wavelength of 250 microns. So, we load that, right. So, now there are two catalogs. I will open each one of them and show you. So, both of these catalogs have several thousand entries. Okay. So, this is now the XMM LSS Swire catalog. We have looked at this previously in some other module, and this is a new catalog which we have never seen before, which is the radio catalog of radio sources in the same part of the sky. Okay. And this also has some coordinates, okay, and it has some flux measurements at 325 megahertz and so on. So, now what do we do next? I want to ask the scientific question. I want to know which are the radio sources which also emit in the X-ray. What is the easiest way to find this out? The easiest way to determine this is by simply matching the catalogs positionally. In order to do that, I click on this icon which has two match sticks over there, and my goal is to create a new table by positionally matching the radio and X-ray catalogs. So, it asks me what kind of algorithm I want to use for the match, what is the match radius. I am going to increase this a little to 2 arc seconds, and it asks me what table it should use as its first table. So, I tell it okay, use the radio catalog as your first table. It asks me what is the name of the column containing the right ascension and the declination, which I specify, and then for the second table I use the far infrared catalog, and again I specify which columns correspond to RA and DEC and what kind of match I want and what is the joint type that I want, which means I want, when I say joint type 1 and 2, it means I want you to combine all the columns in table 1 with all the columns in table 2 for all the objects that have a match. So, I click on go and it found 151 pairs and created a new table which is called 3:match 1,2. It has 151 rows. So, now if I go back to my list of tables over here, I find that a new table has appeared which is called match. Now, I can open it and you can see that the first few columns actually come from the radio catalog, and the next several columns then come from the far infrared catalog. So, now I have actually combined information from a radio catalog with the corresponding information from a far infrared catalog. The fun does not end there. Now, I can of course plot any parameter against any parameter, but I am going to do something else now. I am going to load up an image. So, what I have done now, I have loaded an image of radio image taken again with the GMRT of the same part of the sky where we had loaded the two previous catalogs in TopCat and matched them. So, let us go back to TopCat and see how one can send a table, a match table in this case, from TopCat through to Aladin. Okay. So, all I do is I click on this interop button, send table to Aladin. Aladin is already been detected as an application that is running on the same system, and SAMP will take care of the broadcasting process. It has sent it, there is some error, but there are now a number of sources that have appeared on the. So, I can go here and I right click and I go to properties and I maybe change the symbol to circle, I increase the scaling factor and I change perhaps the color to red. When I do that, I now have a red circle around each of the data points that have been broadcast from the TopCat catalog through to the Aladin application. If I click on any of those data points, in the bottom I get the row entry for that particular object. I can therefore gather a lot of information about its radio and far infrared properties, which are all listed in the columns that you see at the bottom. And you can of course on each of these sources, as I showed you previously, hover and therefore, try to get more information about that source if it is available in SIMBAD or any other catalog. So, what we have seen here is an example of how you can combine information from two catalogs at two different wave bands, in this case far infrared and radio data, match them and send the matched source list through to another application, in this case Aladin, which is showing an image of the sky possibly taken at a third wavelength or third frequency. So, together TopCat and Aladin are very potent tools for analysis of astronomical data in various formats and of various kinds. There is another alternative to Aladin, which is called DS9. I am not going to demonstrate it here, but I just want to mention it. It provides many but not all of the features that Aladin has in a very fast and lightweight interface. Okay. If one takes a look at DS9, perhaps one should do that, and we will see that it's really very easy to use. I am just going to show it to you very briefly by loading an image in DS9. So, I am going to load the same image of the giant radio galaxy that we have looked at in DS9. So, here it appears. Here is the image of the galaxy. As before, using the right mouse button, I can change the color, contrast, etc. I can jump to various color maps. I can go for the rainbow color map, which we have looked at previously, and I can play around and see the data, zoom in, zoom out, and so on. DS9 is not as powerful as Aladin is, but it is also integrated with the SAMP application like TopCat. So, just like we were able to use TopCat to send a table, a catalog from TopCat to Aladin, it is possible to send a table from TopCat to DS9 as well. I am not going to demonstrate all that. It is a really neat application and a very easy way of taking a quick look at an astronomical image that you have produced yourself using your own data analysis, or you have downloaded from a data archive.